My channel is just Litia Martin, so you can just look up my name and it'll probably be like one of the first things that pops up. My channel is okay. So we are live. And here we go. So we've been talking about circles and ellipses so far. And we've seen the definition of both, but I'm a visual learner and I think a lot of people are as well. So I've created this visual to show you all, to kind of show what the definitions really are. So I have this old cork board here, and what I did was I took a pin here, so this represents the center, and then I took a piece of yarn, just any length, and this represents our radius. So the definition of a circle is a set of points. So you see here, these are all just points. So all of these points are a set, and each point is equally distant from that center point. So I could even find, remember, there's technically an infinite number of points between 2 points, right? I can pick any infinite number of points and put another pin in here. And so that would create a circle. And the more points that you put, the more you can see that circle kind of coming together. And so these are all the same length all the way around. So that's the definition of a circle. It's a set of points that are equally distant from one specific point. Now, the ellipse has a little bit of a different definition. Oh, we got some more people joining us. Let me admit and make note here. Okay. So for the ellipse here, what we need is 2 fixed points. So you see in yellow here, that's what we call our foci. So these are the focus points. And then we have 1 length here. So this is just kind of a random length. I could have made this string longer. I could have made it shorter. But the idea and the definition of an ellipse is that you take this measurement, and it's the set of points that is formed with that same measurement, taking the distance from each focus. So for example, here we see this distance here from this focus to that point. Well, then this distance here from that focus to that point is going to add up to give us the length of this string. And so the string is never going to grow. Oops, I lost my focus. No. Let's see. That might be the wrong spot. Yeah, that's the wrong spot. Hang on a second here. We can fix this. Okay, there we go. That kind of works. So I should be able to, I don't know, now that I messed it up, that might not work. Take any point and it'll match up. I think I may have just ruined all of my hard work. Let's see. So that matches up there, right? And then we can pick another point we can see on this end. So it's the same distance, so that leads us to that point there. And we can pick and create any other point along the way. And if I kind of just follow this path, if you remember the animation that I showed you in class last time, then this is what you were seeing. was this kind of movement of this measurement here. And so that creates the shape of the ellipse that we see here. And what I did was, you see the different colors in blue here. These are the co-vertices because they're the shorter side. And then this is the vertices because it's the longer side. And if I flip it, right, these are still going to be the vertices because it's still the same side, but now it's vertical rather than horizontal. Okay, so that is just a quick little kind of demonstration of the definition of the ellipse, right? The idea is that this string is not going to grow or shrink. So it's the same measurement all the way through, and that's what helps us to find these different points that create then the ellipse. Okay, so those are the two definitions of those two shapes that we've been looking at. We are going to watch a quick video now showing a example of an ellipse in the real world. Some of you talked about it in your discussion posts, but we're going to watch a little demonstration. You may have seen a real world example of ellipses in architecture. So there's some rooms that are shaped as ellipses. And so we're going to see an example in the White House where you have the elliptical room and what it does to sound when you're inside of that room. So give me a second here to share my screen. Sorry, it looks like I got closed out of my video, so I gotta open it up again. Okay, let's share this. Okay, so this is, oh, I got disconnected. There we go. This is National Statuary Hall at the US Capitol. Has anyone ever been to this hall? Tap again, see if this works. And I got disconnected. Fun. I might have to just switch over here. Sorry, technical difficulties. Let me just try one more time. If not, I'll switch. Nope, not working. Okay. We are going to switch over. Or I am, you're going to stay right here. Okay, actually, before we watch the video, which I have here, let's talk about whisper galleries a little bit. It was in the video that we saw at the beginning of this unit. So we have some kind of worldwide examples. Close this. It has to do with the architecture of the room. Being in a curved space, sound bounces off of the walls. And so if you are standing next to the wall in a particular spot, which we'll talk about in a second, then you're actually able to hear someone who's far away on the other side of the room as if they're whispering right next to you, which is kind of crazy. I've actually never been in a whisper room. I don't think. I wish I have. But maybe some of you have before. You didn't even realize you were inside of an ellipse. So these are some examples. St. Paul's Cathedral in London. In India. Grand Central Station. The clip is closed, but maybe some of you have been there before. In Spain, Beijing, Germany, the Whispering Arch. So this one's an arch as opposed to a room. But you can see on one end, the little boy is whispering or saying something, and then you can hear it on the other end. So that's kind of another example where the architecture is curved, and so the sound is carried through. The US Capitol building. So that's the example we're going to see in the video, and that's it. So I like this little story here about John Quincy Adams. So it says the dome of the US Capitol building is more than a distinctive silhouette against the Washington, D.C. skyline. When it was first constructed, the structure helped amplify the voices of members of Congress long before microphones appeared on the scene. So that was pretty cool, actually, when they constructed that. They had that in mind, that they wanted the sound to travel. And it says, according to one urban legend, John Quincy Adams pretended to be asleep at his desk while listening to echoes of his opponent's conversations happening in different parts of the room. This so-called whisper spot, now part of the National Statuary Hall, is now designed by an official plaque on the floor, marking the location where the former president sat during his time in Congress. So in the video that we're going to watch, we're going to be with a group that is standing at the plaque, and then you're going to see someone walk away, and then you're going to hear kind of how close it sounds like. So you can kind of imagine that's what it would have been like for John Quincy Adams when he was sitting in his desk and just kind of listening in on other people's conversations. So that's kind of cool. We're gonna watch the video now. It's really short, really quick one.
Opposite way. He was president first, then served in the House. And thus far in our history, he's the only president to have ever done that. He was a wonderful speaker, and when he would give a speech, the galleries were packed. But in his 17th year, he stood to give a speech one morning and he collapsed with a stroke. He was carried off the floor to a nearby office where he died 2 days later, and his funeral was held in this room. But we've noticed something about the area. I'm going to go to the other side of the room, and you can join me in a few moments. But for now, I invite you to come in close and just lay your headphones around your neck. Please step up close. This room is often called the Whispering Chamber. If you can hear my voice on the other side of the room, please raise your hand.
So it's just a short little clip. I know it can be kind of hard to hear, but she's actually just kind of talking normal over there. She's not yelling, and they were actually able to hear her as if she was up close. So that's just kind of one example of an ellipse, how it's used in the real world. And so the idea is, I'm gonna pull back my ellipse here, is that the sound, right, is kind of like bouncing off the wall. So you can kind of imagine it travels to this point and then it goes back to that point. You can kind of think of where the group was standing as one focal point, and then where the lady was standing is another focal point. So you can always see that they kind of always just go back to one another. Like the sound will come off of a point here and then it'll just bounce back and forth between the 2 points. So that is one real world example of ellipses, which is kind of cool. And now we're going to go back to doing some fun math stuff. I have a worksheet for you all that I'm going to post right now. It is called Be the Teacher. So what that means is the assignment is technically already filled in. The sorry, let me just pull it up so that way I can show you while I talk about it. Okay. Oops, I stopped sharing my screen. So this is what the assignment will look like. JJ Jones is the student here, and he has taken a quiz on ellipses. And so what you are going to do is you're going to be going through the quiz and grading it. So we see the first problem, it has the equation. So we're given the ellipse and you're writing the equation, you're determining the center, you're determining the points for the vertices and the points for the co-vertices. So you're going to be checking his work here to see that that's correct. And then you're going to grade it. So each question kind of tells you how to grade it. So for number 1, 4 points each for each problem. So the equation is worth 1 point, center is worth 1 point, and so forth. Number 3 is the same. Number 4, we are given the equation and we are supposed to graph the equation, or that's what the student was supposed to do. So you're going to check that the graph is correct. You're going to also check that each of these is correct: center, vertices, co-vertices, and foci. And then the last part here is going to be taking the general form and then writing it in standard form. And then lastly, writing the equation. So given the vertices and the co-vertices, writing the equation. And we're going to actually skip number 10 because they kind of word it weird. So we're going to skip number 10. So I'm going to post this at the end of class. We are going to go over some more examples from the notes so that you can feel kind of prepared in order to do this assignment. So let's switch over here. Let me see if my iPad works now into some examples, some notes. So these are the notes. We already started them on Tuesday when we last had class. Okay, so last time we looked at the standard forms. We saw how to write the equation of each ellipse given the graph. And then we saw how to graph given an equation. So we left off on part C. Let's go ahead and pick up from there, and then we'll look at how to rewrite into standard form. Stylus here. Okay, so this is our equation. It's not in standard form because if it were in standard form, we would have a 1 on that side. Since we don't have a 1, we need to turn it into a 1. So we would need to divide by 36 all the way through. So to each part, we're dividing by 36. So over in this first part here, 4 divided by 36 will simplify to 1/9. So we have x minus 3 squared divided by 9. And then this next fraction, 9 over 36, simplifies to 1/4. So we're left with y plus 2 squared divided by 4 equals 1. So now this is in standard form because we have the 1 on the right-hand side. And from here, we can determine different things. First of all, we can see what our center will be. The center comes from that value and that value, but just remember you want to think opposite. So x minus 3 squared means that we have an x value of 3, and then y plus 2 squared means we have a y value of minus 2. So there's our center, and I can actually go ahead and plot it here. So this is 3, this is -2, so the point is right there. And so the next thing we need to figure out is our vertices or covertices. We can see that this is going to be a horizontal ellipse. How do we know it's a horizontal ellipse? Well, we want to look at the numbers that are in the denominator. So in this case, we see that we have a 9 and we have a 4. Well, which one is the greater number? The greatest number is 9. So that means that right above it, we have x minus 3. X is the horizontal axis. So that means we have a horizontal ellipse because the longer side is going to be horizontal. So remember that the standard form should be squared. Getting a message from Mr. Stevens. Is Miles still here? If Miles is still here, make sure you go to your meeting.
Okay, I'll go to it right now.
Okay, thank you. So at the bottom here in the standard form, we have a and b, and they're being squared. So we need to unsquare them so we can figure out what that a and b is. In this case, the square root of 9 will be 3, right? It's the same thing as 3 squared. And 4 is the same thing as 2 squared. So that is telling us the distance from the center in either direction. So along the x-axis, it's going to go 3 in either direction of the center. So let me draw that out here. This is my center. I'm going to go 3 to the right and then 3 to the left. So those are my vertices because they're on the longer side. And then my covertices, I'm going to go 2 in either direction, up and down. And there we go. We know that it's up and down because it's underneath y, right? Y is up and down, x is left and right. So once we got that, then we have our ellipse. Okay. Let me know, please, if you have any questions as I'm going through this. we are going to be going into the next part, which is writing the standard form from the general form. But before I move on, are there any questions here? Let me know. So we have 9x squared plus 4y squared plus 8y minus 32 equals 0. We want to write this in standard form. So the steps are actually all the same as it was with the circle. So here's our time to practice that. What we need to do is get all of our x's together and then all the y's together. So we actually only have one x term. So we'll put that there. And then next is our y terms. So 4y squared plus 8y. And then I'm going to leave a little bit of space here. That 32, I'm going to add it over to the other side. Okay. Here's where we have a little bit of a difference between the circle and the ellipse, or between the examples that we've seen before at least. Here we have a coefficient in front of both of our square terms. And we do not want to have coefficients when we are completing the square. So actually the first, with the x term, before we do anything else, that one's already a perfect square because there's no other x term that goes along with it. So we already know that this is just x minus 0 squared, and that's our perfect square already done. So really it's just the y's that we have to complete the square for. And we got to take care of that coefficient. So what we do first before we go into completing the square is we need to factor out the value of that coefficient. If it's a 4, that means I'm going to factor out 4 from both of the y terms. So I can take out the 4, and that leaves me with y squared plus 2y plus blank equals 32. Okay. Notice the blank is inside of the parentheses. That's going to make a difference in just a minute here. But once you notice that there's a coefficient, you factor it out. Now we can just complete the square like normal. So what does that mean? That means we look at the middle term, in this case 2y, divide it by 2, and square it. So that gives us 1 in this case. So I'm going to be adding 1 here. And here's where there's another little change. Normally we would go ahead and add 1 to the other side, but remember we factored out the 4 that's here. So actually, if we were to distribute that 4, this isn't actually a 1, it's actually a 4. Are you not in class? So I'm going to add 4 to the other side instead of 1. So you always, if you factor out a coefficient, once you find your new value to complete the square, when you add it to the other side, you need to add whatever those 2 multiplied gives you. And that's because we want to maintain the balance. So if you were to only add 1, it wouldn't be balanced enough because technically that's not a 1, it's technically a 4 if you were to distribute the 4. So that takes care of that for us. Now this is a complete square. The x was already a complete square. Now the y's, we have the 4 in front, and this in the parentheses is the complete square that will become y plus 1 squared. And on the other side, we have 36. Okay. what you should notice now, hopefully, once you do that, completing the square process, for the most part, you'll always end up with some number on the right side. And basically what we've ended up with is something like what we see here, right? And so how did we take this and turn it into a standard form? All we did was divide by whatever number we have on the end there. So again, we have a 36 in this case. So I'm going to divide everything by 36. And now this will be x minus 0 squared divided by 4 plus y plus 1 squared divided by 4 equals 1. That is our standard form. So from here, just like we did in the previous example, we can determine the center, which in this case will be 0, -1. We can, oops, I made a mistake here. Sorry, there should be a 9. 4 over 36 is 1/9. So that's a 9. We have our center, and then we can figure out our vertices and our co-vertices. So the vertices come from the longer side. The longer side in this case is going to be along y. It's going to be up and down a vertical ellipse because 9 is the bigger number, it's the bigger denominator, and it's underneath y. So if I were to start to graph this, we have the center at 0, -1. And then our vertices are going to come from going up and down by 3 because 3 squared is equal to 9. So I can go up 3, that brings me to 2, and down 3, that puts me at -4 here. So those 2 points, I'm just going to write them down here. They are 0, 2 and 0, -4. So there's my vertices, and then my co-vertices. If I have a 4 underneath x, that means I'm going to go 2 to the left and 2 to the right from the center. So I'm at my center here. So there's 2 to the right, and there's 2 to the left. So those coordinates are 2, -1, and -2, -1. All right, so there are the vertices and co-vertices. Are there any questions so far? I know I've kind of just been going through everything. So the coordinates, I just plotted them. So we find the center first. The center is kind of like the guide to either direction. So once you find that center, then you need to determine how far out you're going to go in either direction. So in this case, we have a 4 in the denominator. 4 is the same thing as 2 squared, and it's underneath the x term. So that means from the center, x is left and right. You're going to go 2 to the left and 2 to the right. And so I just counted out 1, 2. There's that point. 1, 2. There's the other point. And then you just look at the coordinates of that point. For the vertices, that was the co-vertices. The vertices, because it's the longer side here, right? We have 9, which when you square root it gives you 3. And it's underneath y, so you know you're going to go up and down by 3. So 1, 2, 3, 1, 2, 3. There are your 2 points. And then you just look at the coordinate plane to see what those coordinates are. You're welcome. Are there any other questions? We have one more example that we'll do really quickly since we just have a few more minutes left. So in this example, we're just going to have to complete the square twice because we actually have two x terms. So that means we have to complete the square there. And then we have two y terms. So we will need to complete the square here and add the 3 over. Okay, so we'll go piece by piece. This first part, we have x squared. There's no coefficient. There's no, well, technically your coefficient is 1. So we don't have to factor out anything. We can just go ahead and take that middle number, divide it by 2 and square it. So that's going to give us 9. And we're going to add 9 to the other side. And then we are going to complete the square here, but before we can do that, we have a coefficient of 4 that we need to factor out. So over on this side, I'm just going to rewrite this to keep the spacing. I'm going to factor out the 4, so we have y squared minus 2y plus blank equals 3 plus 9 over there. We're going to complete the square. Just take that middle number, which is -2, divide that by 2, and then square it. So that's going to give us 1. So again, on the other side, what this means, since I have the 4 there and the 1 here, if I multiply those together, I get 4. So that's why I have to add to the other side. Okay. And now we have our complete squares. So this will be x plus 3 squared. We have the coefficient 4. This will become y minus 1 squared. And on the other side, we have 16. Okay. We need to take one more step, our final step, to make this standard form for the ellipse, because we need to have the 1 on the right-hand side. So we will divide everything by 16. For x plus 3 squared, since there's no coefficient, that just stays a 16. 4 over 16 will become 1/4. So we have y minus 1 squared divided by 4. And then 1 is on the other side. And that will be our standard form. And we can see that this would have to be a horizontal ellipse because the biggest denominator is 16, and that's underneath x. So that's telling us left and right is going to be our longer side, up and down is shorter side. Okay, so that is going to be it for today. I will post that Be the Teacher assignment. That's going to be your homework for the weekend, and we'll go over it when we get back in class on Monday. Have a great weekend, have a great rest of your day, and I will see you all on Monday.
Thank you. Bye.
You're welcome. Goodbye.